Ok, resumiendo un poco quello che si era visto l'ultima vez, había llegado a varias situaciones del plano. We discuss how the central point of the stars are moving in the diagram density temperature to see how is the evolution of this position. We check several situation. We check with the pressure to see where each piece of the gas is important, where is the ideal gas is ruling, when the radiation pressure are more important of the gas one, and where is start the degenerate gas to be important source of pressure. It's always considering because they are essentially the three mixed, because as we saw, ion stay essentially always in ideal gas. The generation is just at the end when we arrive at the neutron star. It's not more also ions. The radiative pressure can be negligible, but there is always. But only above a certain temperature it's really important. And then from a certain density, electrons start to be more and more degenerate, so their pressure starts to be always more important respect to the total pressure and demand on the equilibrium of the core. So an example of this evolutionary track, considering a curve starts with 0.1 solar masses, 1, 10, 100. Here is a little more correct, considering that it's the core evolved more on his mass than the total mass. So why, if you just consider one mass as total, will go outside will reach the helium burning in the ideal gas. Here we see that there is a turn and going to the degenerate state. Here is not just theoretical, not considering the evolution actual of the core of the stars, just considering that it's fixed, it's the core stay with the mass and evolve with the mass. So here the result that one solar mass is does not arrive at the helium burning and just then evolve as a compact object, and later so will be just a white dwarf of the helium. Actually, the real evolution track of the center is a little more complicated. Here you can see are not perfect straight line because the star doesn't maintain a perfect behavior. They are not perfect polytropes. You're just considering several polytropes altogether. And then also you can see one solar mass. In this case, there is this small deviation because of the contraction when started the hydrogen burning is not perfectly expanding, contracting in a homology way, and we have this more curvaceous movement. So when we see that the star evolve, yes, the core for one solar mass will start to be degenerate, and so its contraction stopped there. But outside there are other the shell burning hydrogen, and so continuously to fill mass to the core that permit to arrive to burn helium in degenerate state. There will be what we see called the helium flash, the burning of the helium, and then finally it turn down and evolve as a white dwarf, but in this case of carbon oxygen, not of helium. The real, you can see it's really more complicated because the star, let's say, is not a perfect polytrope. This evolution is not just one model, several. You have to match them, and so also each part is not isolated. We just mentioned the core will receive mass from the shell, so there is this deviation from the actual, and you can have manage to burn other element, even if theoretically at the beginning should not. Well, reason. Something that's said about to analyze the evolution of the star, the position of the star in another plane that is possible in the Elton-Russell diagram, effective temperature against the luminosity. We look again at this plot, we can see something we mentioned before, something familiar. Here you see the plot of the mass up to a certain fraction of the radius, total radius, respect to the total mass and this fraction. So here we have half of the radius of the stars. Here it's more or less 1/4. And you can see how this fraction of the respect to the total mass vary with the respect to the ratio of the fraction of respect to the total radius. You can see that for 1 and for 10, the behavior are quite similar, almost similar. Then, if you look at the plot for density, temperature, you can see that more or less the two curves for 1 and for 10 are quite similar and remain essentially like just a shift. Here, nearby of the surface, change, but mainly in the temperature, it's more obvious. Is just a shift. This is important because so we're saying that m respect to the total mass vary in the same, doesn't changing with the mass, and the density and temperature have just a shift in since a shift in logarithmic. That means that if you put together, means that the ratio among the two density are the same value value of mass respect to the total mass is just a constant. This is something that we heard before. If you remember, I mentioned you that during the studying how we model stars about the homology relation. That and the homology relation are based essentially on this point. That if we are considering the stars are homologous, and then the behavior of the mass respect to total mass are the same, moving changing in homologous are the same in homologous point, that are the ones that are same fraction of the total radius. This permit to having a solution to transmit the solution on other solution, other situation. We have, as I said, the assumption condition are identical for all the stars, so it's quite reasonable that we can have one solution can be transformed for other further condition. If we just change the mass and the radius, the solution should change accordingly. The homology relation it's a big work. I don't remember if here, yeah. Essentially, you redefine this ratio for the mass, the ratio of the radius with the two parameters, and so on, the ratio for all the other properties, physical properties, density, production of energy, luminosity, and so on. Putting the given a solution, putting the new the other value, because we can substitute the rho with d multiplied rho prime. We can have another system, but since also the other stars respect the same equation, because density, pressure, luminosity, all the other have the same relation for hydrostatic equilibrium, the relation among luminosity and energy production rate, magnetic mass, and so on. We can have just several equations of this additional relation variable equal to 1. From solving this system, we can have several relations among the new several exponent and relation among the properties, considering all the conditions that we suppose. Usually we start with considering the equation of the state for the gas, the opacity, what kind of law is following the opacity, and the energy production rate respect to density and temperature. Here, before I show also another example, here we are going just directly with what could be medium stars, 1, 2 solar masses, that we consider in ideal gas with an internal, the opacity is just a constant. This means that we are considering the opacity is electroscattering. It is quite good if the temperature is quite high, and we saw here that essentially almost all the 6.5 mean 3 million degrees. So we have almost all here is 95% at least above million degrees. So almost all the stars, also from one solar mass, is above the ionization limit. So we have all the gas essentially ionized. So essentially, we don't have opacity to bound free, or just small for the heaviest element. So we consider that is mainly the Thompson scattering, the electroscattering, as a source of opacity. That makes sense. If you put inside this the condition, we got the Z that was this exponent that is connecting with the radius at this value, and since that lambda is mainly 1, we just put 1 and keep nu, that is the exponent for the temperature. Only in certain nuclear reaction or more, with the heaviest element, the density can change. Remember, these coefficients are not exactly real. Is not the equation exactly this. We simplify this equation in this way, and to have simple calculation and just the density and the temperature related to the certain coefficient. Here we can see the nu vary from 4 to 18. This value from proton-proton to CNO is changed in this way. From this the homology relation, we got that we have exactly this one. The relation, the ratio among the luminosity is equal the cubic power of the relation among the masses and the relation among the molecular mass that is connected to the composition. For the radius, we have this relation that is not fixed, depends on Z, and also mu on with Z prime. If you put together, knowing the luminosity depends on the radio, the temperature, effective temperature, and putting together, we can have a relation among the luminosity, logarithmic of the luminosity of stars and the effective temperature. You can see that there are this part here that vary with the Z, so vary with the type of the nuclear reaction involved at the temperature of the core. For nu, like 4, proton is 5.6. For CNO, we had 8.4. That means okay, this is start modeling this part of the Russell diagram. For lowest mass stars with the proton-proton, the slope is a little more less steep, while for more massive stars, the slope of the Russell diagram is steeper. That I think. Then, okay, at the low there are, it shows steeper. Oops, no, I'm. Yeah. So the homology relation manages to show the actual behavior from the Russell diagram and the change of the slope from more massive stars and less massive stars. In the lowest, you saw they are going to steeper, this for other reasons that we'll see later. In the time on the main sequence, that what we are seeing here, but you consider just ideal gas, so the stars in the ideal gas, no degeneracy, essentially also everything is behaving well. The time in the main sequence is more or less exactly the time of nuclear reaction in the for the hydrogen that we saw, that is more or less 10 to the 10 anni years, multiplied by the mass in unit of solar masses, divided in luminosity in solar luminosity. This is because the time on the main sequence depends on how much fuel you have and how much energy you are emitting during the main sequence. In here the mass that is constant comprehend all the part, and considering that we are considering just a part of the total mass, not everything, just the core, and that hydrogen is not 100%, but just more or less 70% for solar abundances. Original abundancy 75. So we got that the time for on the main sequence for a really low mass near the lowest mass, the minimum, 1 point solar masses in 10 to the 12 years. Just remember that the universe have an age of 10 to the 10. And the smallest stars arrive to live 100 times more than the entire universe in the main sequence. That means that all the stars of this kind of form at the beginning are still there. While if you consider for 100 solar masses, almost the limit, we have that is just 1 million years, the time that they are spending on the main sequence. And more or less, yes, this more massive stars are really fast in their evolution. In fact, it's not so easy to see them in clusters, simply because during the time the cluster manage, all the stars manage to evolve and be seen as a real cluster. usually it's already past several millions years, and so the more massive stars are just evolved. Taking the homology relation for the internal temperature, we have this relation among the temperature of stars and its total mass. Respect to homology is always in the ratio of the property of one star respect to the same property of another star. So we can take the value of the sun as the other value, and so we can have a nice calculation. We have this relation for the central temperature among the temperature and the mass, and knowing that for a nuclear reaction we need minimum temperature of 4 millions of Kelvin. Kelvin without the simple degrees or saying Kelvin degrees Kelvin, something like that, because it's more or less in the 79, the sign was absolute degree. So when you're talking about Kelvin, it's well defined that you are talking about degrees, the absolute value, so don't need, you don't have actually. Putting this condition here inside, we got, as I said, that we need at least a minimum of 0.1 solar masses to start to produce the nuclear reaction. Then with the luminosity really low, or just 1,000th of the luminosity of the sun. Actually, we can see here that one of the problem of the low stars is that they are going to really nearby the degeneracy part. So several stars, when they are too small, one of the limits is just that the stars start to be degenerate inside, so doesn't manage to contract more and cannot increase its temperature because it starts to be in a degenerate state. And the gas manage to contrast better contraction. Then we just consider some changes, because as said, we consider opacity that is constant, electroscattering that is for high temperature. But if you are going to lower, less massive stars, we don't have this start to be lowest temperature also inside of the envelope. So we, if you shift and consider a Kramer opacity instead of constant opacity, we have a change in the homology solution. And we got this one. The luminosity goes with the mass to this exponent. You see, it's quite often. Just considering the proton-proton, because we are considering with lower temperature, so temperature where is lower is not definitely we have the carbon-nitrogen cycle, because you see that the sun that is doing essentially in proton-proton if I remember, the production for the sun in particular UCN is few percent. It's negligible, so we have low temperature. The sun is already in a good approximation for keep it all just electroscattering in the side, and it's definitely there is no CNO, so we just consider this case. We have 10.5. If you consider higher temperature, the radiative pressure starts to be more important. So it's not perfect ideal gas. We just introduce a correction. And for really, for when the radiative pressure is really, really high, we have that the luminosity goes essentially linearly with the mass. And this is something that is more or less seen. You can see here we have the approximation, more or less, the plot data of approximately 3. Here written in solar masses, so more or less half solar mass in above. We have approximation for 3 as the general one. If you go at lowest, we have approximately 5 as found in the solution. Even the lowest, no, this is the solar masses, so this is the 10 solar mass. Here in the lowest part, actually this sun should be, is not perfect as so, but if I go in here, for example, they are essentially similar. You can see they approximate just with 3.3 everywhere, and here with them with M on the same range. The data that fitting with the data also depend on the data and on the way, because here we put up to this value the more or less 3 feet. But essentially, it's something that we notice that for the central part of the little highest value of the masses, the luminosity mass relation is more or less cubic, with highest here put 100 masses, here put above 30 solar masses. We have more like linearity, and for the smallest one is steeper, and the luminosity decrease quicker with the mass. Okay. Just to show using the one from Dina, because I found the other. As you show, we can have the evolutionary track for the center in the plane with the temperature, in this case the density. This we are seeing one point center and see how it should evolve. This is quite similar to what we see in the Russell diagram for the was here. That for several stars there is this evolution. This is in training sequence, but considering just one mass and see how evolving with time. In the same way, we can do see another situation. See how the whole stars moved are in the plane. So what is more the isochrone for stars? See how is the evolution maintained at the same age for everyone and just changing the mass. In the stars, we can take all the point, changing just the distance from the center, and see how they are, each point are located in the density temperature diagram. It's the same equivalent of the isochrone, more or less. We have structure lines that plot the position for each value of the relation of mass on total mass or radius mass up to this distance and on time and radius. The real structure is seen for the evolution are not the nice line. This is, as I mentioned before, the stars are not one polytrope. A polytrope have a structure lines that is perfectly a straight line from the surface to the center. Just are shown here. This is really simplified, but we can have a straight line that here the center, the core, and then going to the surface. Obviously, it's going down and down and down and down because usually on the surface we have a density of -6. The sun has more or less the logarithm is -6, and the temperature is usually around the logarithm 4, not 3. For the sun, for example, for this one it is more or less 10 solar masses. Yeah, it's also 4. So you just consider that are more or less here and this size down here. We can draw this line and consider several evolution of the stars during considering each line from each phase of the evolution. These are shown forming sequence for the evolution during red giant, horizontal branch, that is when they are burning the helium, asymptotic giant branch when the phase post burning in the center of the helium, supergiant that are when are burning all other elements, and then the line structure for the white dwarf. You can see the center is degenerate, but we have a small part here outside. For the white dwarf, easily you can have all the you can plot almost all the line in the plot, since usually a recent form white dwarf have a surface temperature of 100,000 degrees, and the density is really high because you have this, essentially the white dwarf is just what remains the core of original stars, so a core in degenerate state, really compact, and a really small shell of hydrogen that is above and stay there. If you do a check, essentially you can see that the point here exactly are following the evolution track for one time solar massive. The line, in fact, is moving because the core is evolving and every point is evolving accordingly. It's also nice, this situation, to see something that is quite obvious. That when, for example, a star here in the horizontal branch, they are burning helium, are obviously also burning, there's a part that are burning hydrogen. This is, as already mentioned, continuity. If you have one point, the temperature has to be continuous, because if it's not continuous, you have a discontinuity. That means a really strong gradient. That means we have a really strong diffusion and will be a movement. There will not equilibrium. And anyway, with a really strong gradient of temperature, we have equilibrium because the energy will flow really quickly and very smooth everything. So if you the center has a certain temperature, the surface is definitely below. We need to have a point which whose temperature is exactly the temperature for the burning of the hydrogen. So when it's burning one element, below there are several shells that are burning all the previous fusion. So it's burning in the center helium, there's a shell burning hydrogen, it's burning carbon, there is a shell for the hydrogen and the helium, and so on. Each shell are producing fuel for the more internal shell. This also means that if this shell is really quick to burn, then could turn off and wait for new amount of fuel. That is something that is so essentially for the synthetic giant branch, because they are this turn on, turn off of the helium shell. So I said the internal point can be in different phases. While the core is burning one heavy element, outside are burning, sorry, the phrase doesn't make a lot of sense, but the outside are burning all the other elements, especially helium and hydrogen. So what we means is that also that since at the beginning it's burning hydrogen, then helium, and so on, and you need to produce all this fuel, that means also that for several times the core is devoid of the current fusion fuel, so the core started to not produce more energy. This causes a contraction of the core because it's part of the, it is also in the equilibrium is the energy produced by the core. So this, the star will start to contract and increase its internal temperature. To burn the new element that actually is, usually we also say that the star need to contract to produce, to burn. Actually, it's contract to maintain the equilibrium. As a consequence, the temperature will rise enough to burn all the other elements. it's not the aim of a star, or it's to burn elements. It's just a physical system try to stay in equilibrium. The contractions we consider that is quasi-statically. That means the time that happen the contraction is definitely bigger than dynamic time. That means that the gas managed to correct internally all the properties to maintain the equilibrium. So contract is not just abruptly, it's contract and reduce the temperature, pressure, density to maintain the equilibrium. So if the hydrostatic equilibrium is valid, the Vira theorem is valid, and we can use it to study how it is working. This is essentially what happened for the red giant and why stars move from the on the main sequence to be a red giant. And just curiosity, usually the stars on the main sequence are defined and dark as luminosity type. Even if all stars are really big, can be 10 solar radius, but it's not definitely dark, but it's called in this way. As usual, we just consider and see that the energy emitted in the time of the contraction usually is smaller than total energy. So we consider that the total energy doesn't change a lot during the contraction. That means that so the energy is conserved. By the Vira theorem, we know that since the Vira theorem, the total energy is connected to, can be seen as both as less the internal energy or one half of the gravitational energy. But so if you derive one, we get that if the total energy is constant, then both gravitational energy and internal energy are conserved separately. It's not that the sum is conserved, but they conserve separately. So gravitational energy must conserve and internal energy must conserve. So if you have the stars that contract and start to heat up, that means that if something contracts, something needs to be expanded, and something heat up, something needs to cool down. So if the core increases density, so it decreases the radius, increases temperature, so the envelope will decrease the density, will increase its radius and decrease its temperature. And this was what caused the giant, the core collapse and the envelope expand, going to something really big, because a giant arrived and the sun will change from one solar radius to another. Essentially can arrive up to the more, arrived up to the orbit of the Earth. That is like 200 solar radius. Briefly, if you consider in one point at are zero with the two little masses nearby, one of the envelope, one of the core, one goes to collapse, the other goes up. We have that the gravitational energy, the potential is this one with the minus, okay, it's absolutely. To the two masses by the potential of in here in this position at R0. Then they're moving one to R1, the other in R2, so the potential will be this one. Considering small variation, we consider that the mass at R0, R1, R2 are more or less the same, so the potential is similar. We can just simplify this part, and so we have a relation among the two distance of the two masses. So if one goes down, the other goes up, and this is okay. This is here will be 1, but this means you can see if the first decrease 10%, the other increase a little more, of 0.25. If 20%, nearly 30%, so is a nice increase in the expand. For a small contraction of the core, the envelope will expand quickly. It is something we noticed. Then, actually, usually the nuclear luminosity internal can be highest than luminosity outside. So the internal energy can increase. So the envelope, the expansion even more stronger. And if since the temperature of the envelopes goes down, we definitely are not more in opacity for constant. We are going for opacity in bound free and bound. They are really stronger, so that means there will be block more the radiation, so we deposit more energy in the gas that cause an expansion of the gas. One additional point in all these points, on the discussion here was not really mentioned the mass loss. The mass loss can be really important, especially you will see in the in this phase, a giant and a giant branch. During the expansion, as we said, the envelope starts to be really opaque to the radiation. The luminosity is really high because we arrive at one to two order of magnitude above the original luminosity of star. Easily can be 100 times brighter. The stars during the radiant branch. That means that, if you remember, and the luminosity, that you have highest opacity and highest luminosity, the two arrive to be bring to instability on the envelope, can be easily lost in this case by solar wind. This is also something that you observe really easily once it's just observing the mass of the white dwarf. We have a white dwarf smaller than one solar masses. That means that if there should be no mass loss, that should mean that we have a star of 0.6, 0.5 solar mass already evolved. That is essentially impossible. As we saw in the sun has more or less 10 to the 10 years. That is all is evolution. That start with one solar mass to evolve should be at the limit now for the universe. If it is half, the evolution is definitely higher because it's the square of the mass on average. that mean will be half, mean 4 times longer, and it's definitely not possible to have this solution. The reason is because during the movement, during evolution of a giant, the star will start to lose a lot of mass. So in fact, when it is up again on the horizontal giant branch, the stars will see that is really white, are really bright, is luminous, but is also quite more luminous than before, and with a color whiter, hotter than his original position. That because also since a lot of envelope, we can see better the internal shell where it is burning hydrogen. So here we saw this sum of the part, the basics, evolution of the point internally on the density temperature diagram, and see that are some parts that are not permitted, essentially because are unstable, and the part where the in general is a little more problem. The part where presented the degeneracy that is just good for a cool down, because if you start a nuclear reaction, will have some problem on stability and runaway, nuclear runaway. Now we'll, okay, and not so much. We'll start to see the, in general, the evolution of the stars and the movement on the HR diagram. We saw the essentially fluorescent diagram, temperature, luminosity, just some characteristic, and that studying the structure, we can justify the shape of the main sequence, where the stars are burning hydrogen in the core. Remember, the main sequence is where the stars are burning hydrogen in their core. Essentially, a star is always a star more or less burning hydrogen, because before burning hydrogen is called protostar, as we'll see. When start the hydrogen burning, in that moment is that start to be a star. That is when the arrive in the sequence. Then for all more or less the evolution, there will be this shell of hydrogen burning, more or less, because the last phases in white dwarf usually is this shell will turn off. Could turn on in some cases for a companion that giving mass to the white dwarf. Now we see little star formation from point of evolution, and not all details, and we see a little later the some part more connected with the interstellar map. Star formation, that is quite well known, that is star formation occurs in molecular clouds. The molecular clouds are mainly composed, obviously, by hydrogen, molecular hydrogen. that is the most abundant element. The molecular hydrogen is more or less half of the whole hydrogen in the galaxy. We can have hydrogen in several phases, state. We can have molecular hydrogen, neutral hydrogen, so an atom of hydrogen, and then ionized hydrogen. So hydrogen, just proton and electron. Plasma state, the atom that is formed by one proton and one electron. There could be also some deuterium, obviously. And then when the atoms combine themselves in molecular and at really low temperature, and we have the state molecular hydrogen. Mainly in our galaxy, just to know, the molecular clouds are mainly inside the bulge within the first 400 parsec from the epicenter, and in a range among 3 and 7 kiloparsec from the galactic center. This is the main storage for molecular hydrogen. Then there are also some more part packed in on the polar arms, but mainly is these two locations. Molecular hydrogen said is composed by molecular hydrogen, but not only. There are some also carbon monoxide, where the relative presence is just 10 to the minus 4, 10 to the minus 5, and other molecules like ammonium, carbon monosulfide, and cyanide. Can you see the molecular clouds are full of really healthy stuff? These molecular are important not mainly for the evolution, but mainly to observe. Molecular hydrogen is really symmetric, so doesn't have an emission of monopole of dipole, sorry. Just emit as a quadrupole and need usually 500 degrees to emit. That is quite high because room temperature is 300 degrees, so 500 is quite high. You cannot find the molecular clouds at this temperature, so the emission of the hydrogen is really, really low. What you usually observe are mainly the CO. There is also some in infrared, some telescope have filter to observe this line of this molecule, or mainly in the radio. You can see that's really small. You observe this quantity and then you infer how much is the hydrogen, the mass of the cloud. The molecular can survive if we have enough dust to create an opacity to block the UV radiation. Because UV radiation obviously has managed to ionize atoms, so we definitely to destroy a molecule. More or less. Because ammonium is quite strong. But UV and X produced by really bright stars can ionize, destroy all the molecules. So you see that usually molecular hydrogen needs an opacity and absorption in the visible at least 1/2 magnitude. Just briefly, and we stop to see next on Friday. There are two main types of molecular clouds, the giant and the small. The giant are really big, 10 to the 5, 10 to the 6 solar masses, with a little hotter, 10, 50 Kelvin, and with higher dispersion, velocity inside of the gas. Typical, you see what is nearby of iron, Orion. Orion, essentially the constellation Orion, there is a really big nursery for stars. Almost all the constellation is filled with gas, molecular gas. And then there are these two clouds are present with the giant. And then the small, definitely a little smaller, 1,000, 10 to 1,000 solar masses, colder, just 10 Kelvin, and smaller, of course, dispersion of the velocity of the gas. And example you can find in the constellation of Taurus. The clouds are not uniform, you can find cores and clumps inside. The giant usually have hot massive cores with a radius of around parsec, numerical density of 10 to the 4, 10 to the 6 particle per cubic centimeter. Mass of this course clumps around 10 to the 4 solar masses. The temperature 3,100 Kelvin, and dispersion velocity 1,3 kilometers. The small cores, smallest in the meter, and little less dense, small masses, colder, and more or less dispersion velocity. These ones usually are the ones that produce OB stars, the more massive, and the smallest always the Tauris. They are a type of pre-main sequence stars. They are around intermediate mass, small mass. Also, the sun passes through this phase. The Tauri is a star in main pre-main sequence stars that are in this situation. They are characterized by some kind of instability of the surface. But just to add something, that cloud will also see the characteristic, the greater the collapse, and will do fragmentation. OB stars usually form in what is called the OB association, because it's more easy to find than there the OB association, because you have found a lot of these stars really bright, and there you can see what really well in the OB association, the fragmentation. We'll see the next class that in fact in OB association that is not bounded. Is a solar system not bounded, so the stars are not connected in E. You can find several solar system, stellar system inside, some cluster. For example, the double cluster of Perseus. This pair of clusters, they are connected more or less among them, between them. Is part of the association that collapse, creating fragmentate and create this juice cluster, and also all other stars, single stars, and other solar systems. Some that can be bounded like a cluster, or unbounded and will disperse quickly. Any question? I'll finish here also, because if I start, definitely I have no time to finish in 5 or more minutes. Okay. Well, should be not so difficult today. I leave you to study for tomorrow. See you next time.